In this presentation, we'll study damping in rotational systems. And in rotational systems, the damping will exert a torque which will act to impede the rotation. The simplest possible relationship for damping in a rotational system is governed by the following equation. T, the torque, is equal to minus Ct, the damping coefficient, times theta dot, the angular velocity. For this particular equation, torque and theta have the same positive direction. This form of rotational damping shows up in many types of mechanical engineering systems. For example, in lots of rotating machinery, such as pumps, turbines, and compressors. In the diagram on the left is the shaft of a rotating machine. It has angular velocity theta dot. The bearings acting upon the shaft exert a torque, labeled T, and the relationship between this torque and the angular velocity of the shaft is governed by the equation we saw before, T equals minus Ct theta dot. Many types of bearings are present in rotating machinery. Among these are journal bearings, where a thin film of lubrication exists between the shaft and the housing. The damping coefficient of journal bearings is governed by Petrov's law, which you see here. This law shows that the damping coefficient is dependent upon the length of the journal bearing, the diameter of the shaft, the lubrication film thickness, and the lubrication viscosity. All rotating machinery have some bearings to constrain the shaft and hold it in place while it rotates. There are various technologies that are available, including air bearings, ball bearings, and magnetic bearings. Each of these has some rotational damping associated with rotational motion. It is this rotational damping that is responsible for the shaft slowing when no motor torque is applied to the shaft. Let's now do an example. We have a shaft supported by two journal bearings, each with a damping coefficient of Ct. The shaft's inertia is I, and we want to find the transfer function between a motor torque that's applied and the angular velocity of the shaft. The motor torque is labeled T sub I. The bearing torques are labeled TB1 and TB2. We will choose the same direction for all the torques and for the angular displacement theta as positive, as shown here. We'll draw a free body diagram for the shaft inertia, and I'm showing Ti, TB1, and TB2 all with positive direction as counterclockwise, and this is the positive direction also for angular displacement theta. Now this is a choice I've made. I could draw the arrows going the other direction. This is just my definition of positive direction for each of these variables. Now with this definition, I can then write my equation of motion. I theta double dot equals the sum of the torques, Ti plus TB1 plus TB2. Both bearings have the same damping coefficient, so the relationship between the torque and the angular velocity, theta dot, will be the same for both. So TB1 equals minus Ct theta dot, and TB2 is minus Ct theta dot. The negative sign appears in the equation because the positive direction for torque and for angular displacement is the same, counterclockwise. We then substitute these expressions for bearing torque into our differential equation. This yields I theta double dot equals Ti minus Ct theta dot minus Ct theta dot. And of course I can simplify that to I theta double dot plus 2Ct theta dot equals Ti. We're going to have the angular velocity theta dot be our output, and so that's why. So theta double dot is equal to y dot. Now changing our variables, our differential equation becomes I y dot plus 2CTy equals Ti. We'll Laplace transform this differential equation to find the transfer function. And of course we ignore initial conditions when we do so. And what we'll find is as follows. The transfer function between the input torque Ti and the angular velocity y of s is 1 over is plus 2ct. So this is a first order transfer function between the input and the output angular velocity. Let's look at the zero state response of this system. So we're assuming that the rotor starts off with 0 angular velocity. And then we're going to apply an input. And our input in this case is a constant torque starting at time 0. So this is an input which is a step. And the height of my step I'll make m, which is the torque that's being applied after time 0. So Ti of t equals mu of t. And I show that graphed here. Now, if we Laplace transform this input torque, we'll find that its Laplace transform is m over s. And now we'll multiply that by our transfer function, 1 over is plus 2ct. And that will give us the output y of s, the angular velocity. We'll now inverse Laplace transform that y of s to find y of t in response to this step input. And we find y of t equals m over 2ct times the quantity 1 minus e to the minus 2ct over I times t, all times u of t. And I graph this output here. So what do we see? We're seeing the angular velocity starting off from 0, and then it exponentially approaches a maximum velocity, which is m over 2ct. You'll note the maximum angular velocity of the shaft is dependent upon m and ct. The larger the value of the input torque m, the greater maximum angular velocity, and the smaller the amount of damping, ct, the greater the angular velocity. The rate at which the shaft approaches its maximum angular velocity is governed by the exponential term, specifically by 2ct over I. So, the greater the value of ct, the faster the shaft will approach its maximum angular velocity. Of course, this maximum angular velocity will be smaller in this case. The larger the value of I, the slower the shaft will approach its maximum angular velocity. And the maximum angular velocity is independent of the value of the inertia I. Let's now examine a second example, one with two inertias, and this is a fluid clutch between two shafts. We have inertia I1 being driven by an input torque Ti, and its angular displacement is labeled theta 1. We then have fluid between I1 and I2, and this fluid acts like a damping. Inertia I2 rotates with angular displacement theta 2. The damping exerts a torque on both I1 and I2, and this torque is dependent upon the relative velocity between I1 and I2. Let's draw free body diagrams for our two inertias. For inertia I1, we have two torques acting upon it. There's the input torque Ti and the torque from the damper, Td1. I draw these both with positive direction as counterclockwise, the same as theta 1. For the second disk, I2, I have only one torque acting upon it. It's the torque from the damper, labeled TD2, and I choose its positive direction, the same as the positive direction for theta 2, counterclockwise. We need to determine how the damping torques are related to the relative velocity between the two disks. So let's look at damping torque 1, TD1. I write it as TD1 equals minus CT times the relative velocity between the disks. But I have two choices for this relative velocity. One is theta 1 dot minus theta 2 dot, and the other is theta 2 dot minus theta 1 dot. Which is the correct expression here? Let's conduct a thought experiment. We'll suppose theta 1 dot is 0 and theta 2 dot is positive. So the first disk is not rotating, and the second disk is rotating counterclockwise. In what direction should the torque from the damping be on the first disk? Physically, we know that this should result in a positive counterclockwise torque on disk 1. Because if disk 2 is rotating and disk 1 is not, the fluid will be rotating so as to drag disk 1 to move in the positive direction, the same as disk 2. Therefore, we know that TD1 is equal to minus CT times theta 1 dot minus theta 2 dot. That is, the green box is correct. This allows us to find our equation of motion for the first inertia. And after a little algebra, we'll find it to be I1 theta 1 double dot plus CT theta 1 dot equals CT theta 2 dot plus TI, the input torque. Disk 2 is acted on only by the torque from the rotational damper. And using exactly the same sort of argument that we just had, I can derive the equation of motion for disk 2. That is, I can determine what the torque is from the damper as a function of the angular velocity difference between disk 1 and disk 2. And after I do so, here's the equation I'll find. I2 theta 2 double dot plus CT theta 2 dot equals CT theta 1 dot. For this problem, we'll be interested in the angular velocity of the disks and not in their angular position. So I'm going to define a new variable. Omega 1 will be equal to theta 1 dot, and omega 2 will be equal to theta 2 dot. With these two variables, I can write my equation of motion as follows. I1 omega 1 dot plus CT omega 1 equals CT omega 2 plus TI, and I2 omega 2 dot plus CT omega 2 equals CT omega 1. So we now have equations of motion in terms of the angular velocities of the two disks, omega 1 and omega 2, and the input torque, Ti. Our next step is we'll Laplace transform these equations of motion, and in doing so, we'll let initial conditions equal 0, because we're interested in finding the transfer functions. After taking the Laplace transform, we'll have these two equations, and both of these are first-order equations. The first one expresses omega 1 in terms of omega 2 and the input Ti, and the second one expresses omega 2 in terms of omega 1. So with two equations in three signal variables, omega 1, omega 2, and Ti, we can eliminate one of the signal variables. In our third step, we eliminate omega 1 of s to find omega 2 of s in terms of the input torque Ti. We'll use our second equation of motion to eliminate omega 1 of s by finding it in terms of omega 2 of s. We'll plug it into the first equation of motion, and then we'll have an expression that relates omega 2 in terms of Ti. We'll collect all the terms that are multiplying omega 2 of s. You see this in the fourth step at the bottom of the page. And from here we need to divide through by the terms in the curly brackets. It's important to emphasize that there's nothing deep going on here. All we're doing is algebra to find omega 2 of s in terms of Ti of s. So after we complete the algebra, we find the following transfer function between the input torque Ti and the output angular velocity of disk 2. And the transfer function is Ct divided by s times the quantity I1 I2 s plus I1 plus I2 times Ct. This is a second order transfer function with one pole at the origin and one pole in the left half plane. There are no zeros to this transfer function. So when we plot the poles and zeros in the complex plane, the figure looks like this. Let's now determine how the angular velocity of disk 2 responds to a step torque on disk 1. We can simply do this by knowing the input in this case would be a step, that is Ti is 1 over s. We can multiply this by the transfer function to find omega 2 of s, and then we can inverse Laplace transform, and we'll find that it has the following shape curve. You'll see a transient, and then omega 2 will approach a ramp. That ramp indicates constant acceleration for disk 2. Now I want you to note that y of s will have an s squared in the denominator. It gets one s in the denominator from the pole at the origin of the transfer function, and the other s in the denominator comes from the input signal, which is a step. Mathematically, we know the response will have a ramp in it, and we know this because y of s has an s squared in the denominator. When we partial fraction expand this y of s, we'll get a 1 over s squared as one of the terms. And of course, the inverse Laplace transform of 1 over s squared is a ramp.